All right, so what we want to do here is I do want to show you the shortcut, right? So in the previous videos regarding the linear regression, we showed you how to build the algorithm from scratch. And what we want to do now is show you how to use the pre-built routine. The routine that we're going to use is actually quite powerful. You can actually fit any order polynomial using this routine. Certainly any order polynomial that would be able to be used in some way, right? Very rarely will you see, for example, like 20th order polynomials. At least in physical applications, that's just not something that's typically done. You don't see a data set fit with a 20th order polynomial typically. So for things that are practical, situations that are practical with physical data, this routine is going to be quite powerful. And so if I go back to my original data set here, the function that we're going to use is called Polyfit, okay? And this stands for polynomial fit, all right? And so this is the routine, and the way to use the routine is to bind it to a variable, and I'm just going to use z. Now you can use whatever you want, right? You can call the Polyfit model whatever you want, but to call it the way that we have imported numpy, what we have, so Polyfit is part of the numpy package, so we have to use np.polyfit since we've imported numpy as np. And so now I need to tell Python what set of data to try and fit a polynomial to. And so we start with our x data and our y data. So this is going to say, okay, here's my two variables, the set of data corresponding to my two variables, and I want to fit this with a polynomial. What order polynomial do I want to fit this with? Well, a linear line is a first order polynomial, okay? And so what we're going to do now is we're just going to go ahead and print this. Okay, we're going to go ahead and print z. And if you'll notice, when we print z, right, this gives us an array of two values. The first is the slope, and the second is the intercept. And once again, these agree with the slope and the intercept from Excel. All right. So with that in mind, we're confident that this routine at least is doing what we want it to do. Now, we're going to want to do something, for example, with the individual elements of that list. If you need the individual elements of that list, then you could do something like, say, I want to bind the slope to this value right here, but this value is the 0th element in the array of z. So that slope is going to be equal to the 0th element of z, right? And the intercept, and I'll shorten intercept to b for simplicity, and that is the first element in z, right? Remember that indexes start from 0, so this is the 0th element, this is the first element, and there's only two elements in this array. And so then I could also then say, okay, print slope and b, and I would get, now notice that these actually are carried out to many more decimal places. Okay, notice that those are carried out to more decimal places. Okay, now how do I get the uncertainties, right? So when we come back into Excel and we look at these uncertainties here, how do I obtain what those uncertainties are, right? And the answer is, the way to do this is going to be this, all right? So I'm going to back out of this. We really don't, you know what, we'll go ahead. We'll add another couple of print statements in, so I'll go ahead and back out. So the method for finding the uncertainties on the slope and the intercept that I showed you in the earlier videos when your errors are uniform, and again, this particular method that I'm showing you assumes uniform error. So this is for the situations when you want to use Python instead of Excel, but you're using them for the same function, or to achieve the same result. And mathematically, there's a few different ways you can arrive at the results in the equations that I showed you before. Okay, and one approach is a matrix approach, and this matrix is often called the convergence matrix. And so the Polyfit function has a way to calculate the convergence matrix, and it's defined as COV. Okay, and what I want to do now is then add a statement to the Polyfit to tell it to do something with the convergence matrix. And so I'm going to tell it to calculate the convergence matrix and set that value to true. Okay, so this actually allows the convergence matrix to be calculated. And then the way to obtain the errors is to diagonalize using linear algebra the convergence matrix. And so Python can do this quite easily as well. So the what we're going to do is the function we're going to write, or the routine that we're going to call, actually, more than write it from scratch. The routine that we're going to call is going to do something very similar to as what Z did. So remember, when we calculated Z, it returned two elements. One was the slope and one was the intercept. And the function that we're going to call is going to do the exact same thing. The diagonalization of the convergence matrix is going to be the elements that are along the diagonal are going to be the error on the slope and the error on the intercept. And the way to call this is to square root the diagonalization of the convergence matrix. Okay, so this is the notation that we need. And now the first element of that diagonalized array is going to be the error on the slope, and the uncertainty on the intercept is going to be the second element, the zeroth element and the first element. Okay, the zeroth element and the first element. And so now what we can do is say print. Let's do it this way just for funsies. The slope is so I'm not going to take the time to underline any text in here, but this will just be plus or minus. Okay, so if this works right, we should get a statement that says the slope is this value, and then plus or minus the uncertainty, which would be this value. All right, so if this works, that we should get a statement that says that. That's because I need to bind this. There we go. That should work. Okay. So the slope is etc., 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 plus or minus. And if I want to clean that up a little bit, then I can do something like that. And here we go. So the slope is plus or 1 point whatever plus or minus 0.0499. And so then we can do the same thing with the intercept, and sometimes it's just nice to just copy and paste and then just modify what you need to. So the intercept is string B plus string sigma B. Right. So let's see what this does. All right. And if we want to plot what's going on, then what we can do is we can calculate the model from here, and the model is going to be the slope times our x values plus the intercept. Okay, so now what I can do there we go. And this should give us the exact same plot as we had seen before, right? This should give us the exact same plot that we had seen before. And sure enough, right? Sure enough. Now, this does not have our axes labeled, but again, we can do that if we want to real quickly. And here we go. All right. Now, as I mentioned before, you can calculate the R squared value by hand. You can put the R squared value in manually, but again, there's also a nice routine that will already do it for you, and it's called CORE-COEF, which stands for correlation coefficient. Okay, and again, it's also in the numpy library. So R is going to equal, and R is lowercase r is usually what's the variable used to display the correlation coefficient. The R squared value, just in case you don't or haven't learned this yet, your R squared value ranges from 0 to 1. Okay, your R squared value ranges from 0 to 1. And the higher the R squared value, the more closely to a linear fit your data appears to be. Now, there's a lot of problems here, okay? You should not just arbitrarily trust a large correlation coefficient. There are many ways that you can have a rather large correlation coefficient with a discernibly scattered or bad data set, okay? But when you combine that with the errors on your slope and with the eye test, that's when we really start to gain some significance, right? You look at your data visually in your plot, you calculate the errors on your slope and intercept, and you calculate the correlation coefficient. All of that put together will be what the scientist uses to evaluate the quality of their data. Okay, but here's how it works. So the R-squared value ranges from 0 to 1. The correlation coefficient is the square root of R-squared, or just the R value. So we label it as R, and it ranges from -1 to 1. So -1 would be a perfect linear relationship where y is decreasing as x is increasing, or a negative slope. 0 is a perfectly uncorrelated or perfectly scattered set of data, and 1 is a perfectly positive slope correlation. Okay, so the R-squared value just puts everything on a positive scale and says, I don't care if my slope is positive or negative, I just care whether this data seem to be correlated or not. But here it is. So np.core coefficient, and again, I want to calculate the correlation coefficient for my XY data. All right. Now, don't worry too much about this particular bracket here, okay, this list of 0 and 1. This is just a syntax that's necessary for the code to run. And so I want to print the R-squared value because that's what Excel gives us. And so I'm going to square that. And okay, so if we're going to be truly coherent here, we really should be commenting as we go. So this calculates the slope and intercept from the Polyfit function. Okay. This is the model. This calculates on the slope and intercept, and then we're going to calculate the R-squared value. Let's write it like this. Plot the data. That's how we should say that. Plot the graph the data and format the plot. Okay. So our code is commented, and things should be reasonably clear to somebody else reading your code. And let's see if this works. Oh. We want to print this. Okay, so this should work. And let's see. And sure enough, it sure did. Now let's make sure that this value is what we get, 0.99046, 0.990464, and sure enough, we get the exact same result that Excel gives us. So this is an example of using the routines that are already in numpy to work smarter, not harder. And so if you only need to calculate the slope and intercept of data and you're not worried about their errors, then this is a really good way to do it. And the linear regression is one of the things to spend a lot of time on, because there's a lot of lessons to be learned from this and a lot of examples to be learned, but each of them are very important. So one of the next things that we'll do is I'll show you how to get around importing these or get around typing these in by hand, and I'll show you how to import these from an external file. So, you know, if you have your data, especially if you have, you know, thousands of lines of data, right?